Uh, Welcome everyone. We are very happy to have Sasank Mouli here from IIT Indore. Sasank did his PhD at UCSD. His research interests are in proof.
Oh, that he was a summer intern here.
Yeah. Before that, he was a summer intern here. Sasank's research interests are broadly in proof complexity with a focus on algebraic proof systems. In fact, in the large sort of theory community in India, he's one of the very few people who works on proof complexity, and he's going to tell us about some recent work.
Thanks. So, I'm going to talk about my recent work, which is about this algebraic proof system polynomial calculus, which you can think of as a proof system formalizing most basic algebra, right? But we'll get into what it exactly is. But so it's about this proof system polynomial calculus, which the result is how over two different bases or two different encodings of variables, which we are also very familiar with, like the Boolean encoding is what is ubiquitous in theory CS, that is the 0-1 encoding, and the Fourier encoding is also quite common, right? You encounter it in a lot of these kind of Boolean function analysis and so on, where it's this plus minus one encoding, and this result is about how there is a separation between these two encodings with respect to proofs of this system. Okay, so but I kind of prepared a broader introduction on proof theory, which I think anyway for a wider audience, I thought it would be nice. But this work comes under proof complexity, but the parent area of that, which is the older parent area, is proof theory, which is this. Just to be brief, it is the subfield of mathematics which deals with the structure of proofs and logical arguments, right? So if you have a proof or a logical argument, just any sort of proof you write in mathematics, if you want to abstractly kind of see what is its structure, like what are the rules going into it, how are you making inferences, and a certain proof, what can you say about the structure of sentences appearing in the proof, right? So it has a very rich history, like proof theory. That I think you must have all heard this or read about this, that Aristotle system was the first system which was something resembling formal logic. Maybe before that there were proof or some ideas about logical arguments, but Aristotle, I think, he was the first one. And then there is another good example is, which I think we all get introduced to early on, which I think I got introduced to proofs. My first introduction was in pure plane geometry, where it's a very nice system where you have your inference rules, where you can certain ways to construct geometric objects, right? And you have certain axioms saying that about similar triangles or about right angles and so on, which are very pretty much a logical system. And it's also very rich in the sense about the constructions you can make or the proofs you can write. It's a very rich language. And so that's another early example. But the current proof theory or even proof complexity where we are is due to Frege, where Frege was the first person to look at proofs in an abstract form, right? So these are all more like kind of intuitionistic, or kind of, they were more like how we do make formal arguments in real life. So trying to capture that. But this was actually where proofs were looked at as a bunch of symbols, right? Which is what, in a very abstract form, in current theory language, that's how you would look at it. So there, this bunch of symbols tied together by some proof rules. So Frege introduced this his proof system, which looked at proofs for the first time in this abstract way. And so now now we have many such set of many such proof systems, which are many set of systems where we have some ways to represent formulae and ways to infer formulae. But any such system we can show that it's equivalent to each other, especially if it's like, let's say, a propositional system talking about Boolean formulae, we can prove that they're equivalent to each other. And but we call any such system now a Frege proof system after Frege, because this idea of abstracting proofs came from him. So then
complete there means that the system should be able to prove every true statement.
Yeah. So yeah, exactly. So if you talk about the propositional or a first order logic system, sorry, what's that? If you talk about the first order, talk about a propositional or first order system, then you have completeness, right? So you take any a set of large enough set of inference rules, they will be complete, and such complete system is usually referred to as a Frege system. But maybe we use this thing more for Boolean systems or propositional. I don't know if first order systems are also. I guess yeah. I mean, because I think a Frege system is just a name for this complete set of rules. It could be propositional first order or anything. So then after Frege, so there was Hilbert. There's this famous Hilbert's program which started this quest to kind of automatize the whole of mathematics. Like so to put it in current language, he wanted to find a set of axioms, like a foundational set of axioms, such that if you build a Frege system on top of these axioms, you can kind of automatize the whole of mathematics, in the sense that any mathematical theorem would have a proof in this system. Is it pretty complete for the whole mathematics, or maybe in some reasonable sense you could say that it's complete. We know, we've heard this very famous result of Gödel, which brought an end to this program, and it said it basically said that any sufficiently powerful logical system cannot be both complete and consistent, right? So if you take let's say any sort of real numbers with arithmetic, let's say, and you take some basic set of axioms which derive new theorems. So any such reasonably powerful system, which I think it should just be powerful enough to encode arithmetic. That's all it's needed. And with that already you can Gödel showed that it cannot be both complete and consistent. So either it's incomplete, so there are theorems outside the system, provably, or it's inconsistent, that it's just not a consistent system. Okay. So, and interestingly, so von Neumann later showed that one example of such incompleteness is that a system cannot prove its own consistency. So if it's a powerful enough system, then it cannot prove. So you can encode in the system the statement that my system is consistent. So you can encode that within the system, and that statement itself cannot be. It's outside the system, right? So it's kind of like this barber's paradox, right? The barber shaves everybody who does not shave themselves. Then who shaves the barber? It's actually, there's a very deep connection between this and what Gödel's theorem is. So in a certain sense, it's a very formal way of proving this paradox. I think it ties into this paradox. So and then we know Turing's paper, which introduced the notion of a Turing machine, and it reframed Gödel's theorem as undecidability, right? And then that was really foundational for theoretical computer science. So this is like a brief history of proof theory. So with just the theory of proofs. But after Turing's work and subsequent work, what we got interested in more is not only provability or unprovability and such notions, but also the complexity, right? So these days we are more interested in not only whether something is provable or computable, but what is the amount of resources is what we are currently very much interested in. And so then that's when we move from proof theory to sort of proof complexity, is where we say, okay, it's the theoretical structure is great, but so now that we have this rich theory of NP completeness and so on, and we know that many combinatorial problems can be encoded as SAT problems, and they can be you can run SAT solvers to solve large class of problems which occur in real life. So then we want to know sort of the limits of these SAT solvers, right? So in the sense that whenever this SAT solver solves a particular optimization problem, let's say, then the trace of the solver contains a proof in some logical system, because the SAT solver has to operate in some logical system, right? It's not, I mean, SAT solver ultimately has some simple rules and heuristics which can be formalized logically in a very small system. And then you can say that, okay, if I give you an unsatisfiable formula, let's say the negation of PHP general principle, and your SAT solver runs and tells you that, okay, this is false, right? Then you look at the trace, it must have had a proof that it's false, right? And that proof will be in some logical system. So now what we're interested in computationally in with these logical systems is lower bounds for logical systems, right? Not only these classical notions of what is provable in a system and unprovable, but in fact, what is efficiently provable in these logical systems. And the systems we consider are much weaker and much smaller than these huge systems, right? So what Gödel considered is what currently today we know it as ZFC, Zermelo-Frankel set theory. But what we currently prove lower bounds for these are much smaller systems, because in real life we tend to encounter problems in which are much simpler. So so that's where so let me give a formal definition of the proof complexity or propositional proof complexity. So like I said, it's this proof complexity is this subfield that studies lengths of proofs, right? And a propositional proof system is where the axioms are Boolean formulae, right? So propositional means that they are all propositions, Boolean formulae, the axioms. And then there are some inference rules which allow deriving new formulae, which again, like I said, need not be as powerful as this Frege systems, but can be just powerful enough to be used for our purposes, right? So so to state it formally, a proof system is a verifier for all tautological formulae taught. So you can think of it as a NP sort of a verifier for a co-NP problem, right? So you have a co-NP complete problem, tautology, but what you're looking for is an NP kind of a verifier such that there exist short certificates which are verifiable by this verifier, and the certificates are the proofs, right? So in other words, so you take a formula which is a tautology, then there is a proof which is a certificate such that this verifier accepts this pair, which is the tautology and the proof, right? So sort of we are looking for short proofs of these tautologies. And so the biggest question here is co-NP equal to NP, or can we separate co-NP from NP, right? So if we can show that maybe for any general sort of verifier, polytime verifier, there are no short proofs for some formula in taut, or taut is not contained in it in that sense, then we have separated co-NP from NP. But usually we are interested in much smaller goals, like, because okay. So, and let me just give you an overview of some well-studied proof systems over the past few decades. So resolution is a very well-known system which underlies most well-known SAT solvers. I think just now we are starting to move out of the SAT solvers that are based on resolution, but up until I think the last decade or early earlier this decade, many SAT solvers are based on resolution. So you maybe if you heard of these DPLL solvers or CDCL, even CDCL probably based on resolution. And and then cutting planes is a proof system which captures integer linear programs, right? So let's say you optimize, you solve some optimization problem using integer linear programming. Then if you want to study it theoretically and prove lower bounds, that then you would be in cutting planes. And polynomial calculus is sort of this algebraic system which the core of polynomial calculus is this Grosvenor basis algorithm, which is this search algorithm to find a Grosvenor basis, right? So it's like finding a good basis for an ideal is basically this Grosvenor basis algorithm, where the good basis is in is in certain sense it's if you have that basis, things become easier computation wise. So for this Grosvenor basis algorithm is what underlies polynomial calculus, but you can think of polynomial calculus as, let's say you do some basic algebra and you write a small proof anywhere which involves some basic algebra, then you would most likely be in polynomial calculus. So, and finally, sum of squares is also another proof system which is very very much studied these days, which underlies basically semi-definite programs. Okay. And so maybe okay, so my already 20 minutes in, so I had some introduction to resolution and some basic results, which I guess maybe I think might not have enough time later on. So maybe let me skip through this. So let me kind of cover this very quickly. So resolution is basically this system where you're given some initial clauses, right, which are your axioms, and then you have two clauses, let's say d1 or x and d2 or not x, and you can sort of cut this x and not x and derive d1 or d2. So that's the only non-trivial rule in resolution. And you do this and you say you're given some set of unsatisfiable clauses, then you want to derive a contradiction from it. So by doing these cuts, you want to derive a contradiction, and that's resolution. And let me just briefly say how we get proof bounds for resolution. So the main approach to bounds for resolution is this size width connection, right? So where what it basically says is that so if there is a small proof of resolution, a resolution proof of some formula, then there is a small width proof, right? A small size proof implies a small width proof. Or in the contrapositive, it means if you can prove width lower bounds, then you can prove size lower bounds, right? And so then the problem of
what is
proof,
the size and what is the width?
so you can intuitively, what is size? So let's say you have a bunch of clauses in the proof. So the size would just be the number of clauses. So because every proof line is a clause, because so see, you start with clauses and you cut two clauses to get a clause. So every line is a clause. So the proof size is just the number of clauses. And the width is again intuitive. Width is the width of a clause. So the largest clause you can find in the proof is the width. So the widest, or the with the most literals. Okay. And
So the size is,
yeah,
is it like the number of states that you need in order to get that
contradiction.
contradiction?
Because the thing is, in resolution, each clause is not very large. It can only have n variables, right? So then it's the same thing to count the number of lines or the number of clauses, or any size measure would reduce to the number of lines basically. But if you take polynomial calculus, for example, the size measure we usually take is the number of monomials. So if polynomial calculus is
You will define polynomial calculus shortly.
yeah. But so I just want to kind of say this, that so let's say you have polynomial calculus, and which every line is a polynomial, right? Then here the size measure would be the number of monomials, some total number of monomials, all throughout. But it wouldn't be the number of lines, because here the number of line measure is not the same as the size measure, because each polynomial could be exponentially large. And it's interesting that the number of line measure, if you can prove lower bounds on PC number of lines measure, you get some very big lower bounds in a algebraic circuit complexity. In fact, like the which are kind of separating VP from VNP or something along that direction, because the number of line measure is a much harder measure to, because each line, so if you just talk about number of lines in that thing, then in each line I can pack anything, right? So I can pack any sort of hard functions. I can not for not every system the number of line measure is uh, easy or is the right measure or what the measure we handle, but for resolution it's the same. So okay. So
Why do you define? My question was, why can you patch everything? But I guess you.
sorry, what?
Why can you patch an arbitrary function in one line?
No, because if your size measure
Every
doesn't,
function has a polynomial representation. You write down the whole polynomial.
so
Okay, but it needs to be derivable from the previous line.
That's
yeah, but still if you
the line will be very expressive.
Yeah, that is true. It could just say sum of squares is zero, and that means everything is zero.
yeah, no, but if your size measure doesn't include the size of each polynomial, then deriving between also you have such certain completeness, so you can derive, and as long as you don't consider each line's size, it doesn't matter. Then you can pack huge things in each line and get a very general system. So I think you can probably get close to a Frege system or something like that. So okay.
So would it be correct to say that the size here is this size times width, roughly?
But what is width here? Like
Is the number of
monomials?
Yeah.
No. But here we have instead of width we have degree. So degree of each line, max degree. But here we just call it size. Size is just the sum of sizes of all polynomials.
I see.
So that's because that's kind of the difference between these two systems is which actually is very has a lot of implications in the sense that for example, for things like resolution or cutting planes where each line is very sparse, you can get lower bounds using communication complexity based techniques, because what you need to get lower bounds there is each line needs to be efficiently communicable. Sort of, if you can break up the line and communicate between two parties, you can import lower bounds from there, get lower bounds for these proofs. But it's an open problem for polynomial calculus to get such lower bounds. This communication based lower bounds, because each line we don't know how to break it up and make it map it into communication complexity, because each line has so many monomials. How do you, maybe some number on the forehead or some kind of model, or no, not even number on, no, so maybe some multi-party model actually.
Maybe
So
it will make, I mean, I don't know how many people here are familiar with polynomial calculus. It might make sense to maybe see the definition of polynomial calculus and then,
sorry, okay. So
I know one person is.
sorry.
I know one person is coming here.
no, but there's nothing in the definition. Ultimately it's just a bunch of polynomial lines, right? So that's all you need to kind of. But anyway, so this size width connection, I wrote a proof, but ultimately the proof goes in this way that let's say you have I mean, I'll just talk about very briefly. So let's say you have a large a small size proof, right? Let's say you have a small size proof. Then what you do is you pick a variable that appears a lot in the proof, right? Let's say you want to drop the degree of this proof, and or sorry, let's say a width. Let's say you want to drop the width of this proof, and within this proof you have these high width clauses, right? And you have, let's say, many high width clauses, and you want to get rid of all of these. Then, since each clause is very high width, is very fat, then there is one variable which appears on average in many clauses, right? So if each clause is built W, then there is a variable that appears in W by n clauses by an averaging argument, right? And so then you just set that variable to 0, right? And then you have you kill this fraction of the proof, right? But you also need to kind of take care of this branch where you set the variable to 1. But that you sort of kind of leave it to an inductive argument. So here you say inductively, inductively there are now only n minus 1 variables. So here I don't expect any drop in the size of the proof, but this is all I need. Sort of that one branch, I set the variable to 0, it kills some large clauses and drops the size of the proof. And since I have a bound on the size of the proof, I only need to do it a few times before all the high width things disappear, right? And I don't need to
resolution.
Resolution or even PC, it could be the same, but I haven't defined it. Okay, so okay, okay. So let's say, I mean, we're talking about resolution, and so using this size width connection, we have these lower bounds, which for resolution, which are this PHP, and these are some popular tautologies, PHP and these F2 linear equations, or you can define them over a graph, F2 linear equations and over a graph, something like that, and random CNFs. So these were all proved. I think they were proved directly without the size width connection. Then the size width connection was proved, and they were all reproved by Ben Sasank. So if you want to know resolution lower bounds, this is the paper to read, Ben Sasank, which covers all the state of the art proofs or the lower bounds. So okay, and okay, so then we come to definition of PC, where so PC, like I said, so it's an algebraic system. So your axioms are polynomials, right? Some set of polynomials. So if you have clauses, you encode them as a set of polynomials, right? And a PC proof, what it does is it has these two rules: linear combination and multiplication, right? So linear combination is where you can take a linear combination and derive a new line, right? Or if you multiplication is where you multiply by a variable and you derive a new line, right? So kind of we are working in
the first line are scalars.
Yeah.
And X is a variable here.
Yeah, X is a variable. Yeah. So in a sense, we are working in the ideal generated by these P1 to PM, right? So you have these axioms P1 to PM. You have the ideal generated by them is exactly every polynomial that can be derived from these two, right? But usually we are interested not in the general ideals, but in the degree bounded ideals. So in the sense that what can you derive within low degree? So from the axioms, the polynomial should be reachable in low degree. That's the kind of ideals we are interested in. So, and the size, like I said, is the number of monomials in the entire proof. So you can define it as a sum of monomials in each line, or you can kind of just like a bag of monomials throughout the proof. So they would be the same, but that's the size. And the degrees, again, like I said, is the max degree of any monomial in the proof. Okay. So yeah. So okay. So now
what's the contradiction? You want to finally show one is in the ideal.
Yeah, exactly. Yeah. One is in the ideal.
So you have a bunch of polynomials. You want to show these polynomials are inconsistent with each other.
Yeah.
So the system is you got to keep deriving things like this. You're going to find things in the ideal till you reach the element 1.
1, exactly. Yeah.
So even though 1 is a very small degree, you possibly have to go to a very large degree. It might be the case you have to go to a very large degree and come back to
a small degree, right? Yeah.
So dynamic version of the same case, the dynamic version of the
null set. Yeah. Dynamic version. Yeah. Pretty much. Yeah. So and most lower ones, I think you would know that they go through this medium complexity clauses, and that's where the degree would peak. Yeah. So
why are you doing the dynamic version? Because you derive it step by step, and you can change whatever the boosters have to be right down in one line.
Yeah, it's exactly the algorithmic version of it.
Yeah. So sir, you had a question, I think, or No. Oh, okay. Okay. So, and this size degree connection I mentioned for resolution, size width connection, it holds as like a size degree connection for PC, right? So similar, it's exactly the same. In fact, it was proved first for PC, then it was kind of proved for resolution, and so the same thing. Linear degree implies exponential size, and similar lower bounds were all again proved for PC. The same tautologies, pigeonhole, Tseitin, random CNFs, and Aleknovich Razborov actually also again proved this. United all these lower bounds and gave a general framework and showed that you take any expanding set of clauses, you would get a lower bound. And there is some other caveats on. Okay, yeah, no, I guess if it's a set of clauses, then any expanding set of clauses would give a lower bound. Where expanding means that you have this bipartite graph between variables and clauses, right? Each clause and which clause goes into which variable. So if that graph is an expander, then they showed that PC lower bounds hold. Okay, so the message is that okay, we know resolution and PC well, and we have good lower bounds and good understanding of them. But the kind of current frontier, current the next big problem is lower bounds for the system AC0 P Frege. Or let's say if we take P equal to 2, where so then it's just AC0 of parities. So
in the for the trade-offs,
yeah,
in resolution we have width versus size. Short proofs can be made narrow.
Yeah.
And here, actually, that was got from the original IPS statement, which says that short PC proofs can be made low degree PC proofs. Is that what the?
No, even in the original paper, Clegg, Edmonds, Impagliazzo, there was this thing, I think, which is it was kind of half.
Okay, I don't get it, but this is the statement that was there. That is basically short PC proofs can be made low degree PC. Is that the corresponding statement? That is, by setting a variable, basically this. While here setting a variable, you could throw away the fat clause. Here you will lower the degree of
it's exactly very parallel.
But is there a similar statement in which instead of degree versus size, if you count the width of each line versus size, is there a trade-off or there is no such one?
What is width?
Width is the number of monomials you write for each, because that I don't know how to.
What is width and what then size?
Okay, there's a notion of number of monomials in a particular line and the total number of lines. Here you are using the fact that when you set a variable, this notion of width or degree drops. But if you talk about the number of monomials in a line, there is nothing, I do not know how to make that drop considerably by just setting a variable. No?
So you want that each line is small.
Each line is small,
but the number of lines can be
That
large.
problem they encounter even for just with size degree.
Size degree. Oh, okay.
There's a different kind of argument.
Okay. Okay. Anyway, I'll ask again.
I have maybe a more basic question. So so the previous thing is okay. So what do we want to do? We are given a bunch of polynomial equations. We are somehow trying to show that this set of equations can't be simultaneously satisfied.
Right.
So and we are going to do that by deriving the one polynomial.
Yeah.
Now, I mean, usually for Null-Chern-Zatz type thing, you will need your field to be closed and nonsense like that.
Oh,
so, like for instance, why is this complete when you are dealing with?
No, because it's Boolean. That's the thing. So like there is always a truth table proof. Like that's basically it. So if Null-Chern-Zatz to get a certificate, you're right. You need to be in complex numbers or something. But if all the variables are Boolean, then the certificate.
By variables are Boolean, you mean some of the equations are xi squared equals xi.
Yeah, for every variable you have.
For every variable
you have that.
Okay.
So then you always have a truth table certificate.
Okay.
So minus xi is always to be 0.
Okay.
Yeah, I mean,
talk to that. That's an important part of this program.
yeah, but okay. So don't hold on to that too much. Like, yeah, but okay. So so the thing is, we are currently at this frontier where okay, even with circuit lower bounds, this is pretty much okay. Maybe with triangulars we are.
Not everybody would know what is AC0.
Oh, okay.
So
So
is zero on the top or the bottom?
I mean, I usually write it on the top, but I've seen people write it at the bottom.
You
So
don't write that always.
oh, that. So so AC0 is usually this. So AC0 is this system where or this is circuit class where you have constant depth, unbounded fan-in gates, right? It's a very intuitive system where you have and or not gates, constant depth. The number of levels is constant, but the fan-in is unbounded. You can so we.
No, but what is the AC0 of P Frege proof?
So so it's a Frege system where every line is AC0 P circuit, right? So if you know if AC0 circuits are defined, then AC0 P or AC0 parity circuits are just you can also additionally use a parity gate, right? So now you know that AC0 circuits, AC0 P Frege proofs are where each line is an AC0 P circuit, where usually you have a bound on the depth of that circuit, right? You say AC0 P Frege proofs of depth D, then every line is a proof is a circuit of depth D, and you apply your Frege rules, inference rules, but you never try to build circuits bigger than depth D, right? And I mean you can define your Frege rules and you can restrict them to these kind of circuits such that you're only building these circuits and not building general circuits. Okay, so so the current state is that we have circuit lower bounds for AC0P, right? That dates back to Razborov and Smolensky, which I don't know 80s or something like. But in the proof world, there were lower bounds for AC0. Constant depth Frege, right? But AC0 parity Frege, for example, it has been open since these lower bounds again since the 80s. So so kind of if you know Razborov Smolensky, the lower bound the argument, it goes through these approximating polynomials. So AC0 P circuits are approximated by polynomials. And the polynomials are then used to get a lower bound in the sense that you say that these approximate. So for example, parity cannot be approximated by low degree F3 polynomials. So then from that and then the circuits can be approximated by these low degree polynomials. So that's where you get the lower bound. But in the proof world, we don't know how to transport it. So because there is no notion of approximate line or an approximate true statement, right? Like what is that? So if some function is being captured approximately, then what does it mean in a proof or in a proof line? So that there is a gap there. But nevertheless, since it involved algebraic reasoning, this argument for AC0P lower bounds, the PC was actually introduced, and even Null-Stellensatz as a proof system for propositional proof complexity was introduced to maybe kind of get some lower bounds for this system, maybe some weak lower bounds. So the initial Null-Stellensatz paper actually got some lower bounds for a very weak version of AC0 P Frege, and the PC is one more step like a bigger system. Okay, but now we understand Null-Stellensatz, we understand PC, and that's great. But we still have no clue how to get to AC0 P Frege. It's completely wide open. So and this is where we come to the system in this talk, which is PC not over 0, 1, but over the Fourier basis plus minus 1. So why is this interesting? Because this is really the smallest non-trivial system of PC, which is like AC0 parity, but we don't know, we didn't know lower bounds until recently for this system. Okay, so that's where kind of things stopped, where we knew PC 0, 1 lower bounds. We didn't know AC0 parity lower bounds, but in between was this system PC plus minus 1. Okay, And so no generic size degree trade-off. Yeah.
For Ramprasad's question, both standard PC, every variable you throw in for free the polynomial x square minus x equals
Yeah,
0.
yeah.
PC over plus minus 1 means for every variable you throw in the thing that x square minus 1 equals 0.
Yeah, yeah.
That's the difference between the two. So you have the actual statements, but in addition to that, you have these axioms which tell you your Boolean, and whether it's Boolean is coming from 0, 1 or plus minus 1. That's the
That's a
difference.
difference. Yeah, yeah.
But
So
the difficulty is like the unusual behavior here is you can't do restrictions like you were doing for resolution. Because in resolution,
Yeah.
when you put x equals 0,
yeah,
you kill all clauses in which this appears that way, right? This
Yeah.
no longer happens here.
yeah.
And that is the difficulty of this.
Now, what do you mean by that?
Because you don't kill monomials by just setting things to variables to anything.
And then
Yeah.
x equal to 0 is not a valid operation and you're saying x square is equal to 1.
Yeah, and by setting plus 1 or minus 1 won't kill a term like a monomial. It won't kill. So because it's ultimately it's a parity, right? It won't kill. So, and in fact, something worse is true in that you have a counterexample for a size degree trade-off. Maybe if you are hoping that okay somehow I can get a size degree trade-off not through restrictions but maybe some other means, but you cannot do that because there are these F2 linear equations which have small size over PC plus minus 1 because if they're F2 linear equations, you can encode them easily over plus minus 1 and you can simulate Gaussian elimination over PC plus minus 1. But but the thing is they require large degree because degree as far as degree goes there is no difference between 0 and plus minus 1. It's just a linear shift, right? So degree lower bounds on 0, 1 will hold over degree lower bounds on plus minus 1. But obviously these F2 linear equations are very simple. They are just like Gaussian elimination. So they have small size over PC plus minus 1. Okay, so that's already bad news. So but yeah,
I'm not following. So size degree trade-off is something that says if you have a large proof, it should have it's either a high size or high degree.
yeah.
So why is this a problem? Because you have a large degree proof that is maybe low size, but you have a small size that's maybe high degree.
No. So this is an example which has small size but large degree. So that contradicts this trade-off, right? So large degree doesn't imply large size.
So I think the answer is the generic way. So for example, suppose you want to prove a lower bound or just polynomial. I mean, proving degree lower bounds is going to be much easier than proving sparsity lower bounds.
Okay.
What kind of things would you do for showing that you need this many monomials?
Okay.
So the size degree thing was a great tool because it reduced proving size lower bound to just degree lower bound. And then you can use algebra. Because some are more amenable for
If the
degree.
size is small, then without a generality, the degree is not too large. And then
No. If the size is small, there is another proof with
right.
Yeah.
This is the okay. This is like consider
Yeah, this is like one.
because
This is like Pensasum, some size a bit.
right.
But this was an easy, yeah. So anyway, so size degree was available.
Yeah.
But when you bring in 1 minus 1, this root is gone.
Yeah.
The other thing is also that you can always go from plus 1 minus 1 to 0, 1 by replacing each xi with 1 minus xi by 2.
Yeah.
But that completely messes with the size of the polynomial.
Yeah.
This transformation just might explode.
Yeah. Yeah. And usually degree lower bounds are very combinatorial arguments. So degree lower bounds is where the heart of so because once you want to prove a degree or width lower bound, you can really get into, let's say for PHP, you can say, see, this is what is happening. Let me take a mapping and let me try to, you can really get into the heart of the combinatorics with degree or size width. But with size, like Arkadya said, you have no clue. Like how do I even characterize it? How do I bound it? So yeah. So this was the state until recently when Sokolov, so Dmitry Sokolov, he proved this first lower bounds for PC plus minus 1, and they were for random CNFs and graph PHP. Okay, which actually it turns out like some kind of a little trick or a cheat to getting size degree trade-offs. So it's kind of just a trick on that. So what he introduced, a new notion of degree called a quadratic degree. So just not usual degree, but quadratic degree. And then he introduced a new operation called split, which is like restrictions. So like degree and restrictions are, or restriction, I mean, setting 0, 1. So like degree and restrictions are in the Boolean world. Here he introduced quadratic degree and this split, which is like setting things to 0, 1. And with that, what he showed, we showed the lower one. So let me define this quadratic degree. Okay, much time do I have?
10 minutes.
10 minutes. Can I take a little more time, like, or how does it work?
I can't stop people, but you can keep talking.
Yeah. Okay. That's fair. So quadratic, yeah.
Sometimes coordinators help us the whip.
So quadratic degree is this notion which is like Hamming distance, right? So it's a very interesting notion where suppose you have a polynomial like p equal to something like p1 plus p2 t3 so on dk. The quadratic degree is kind of saying, okay, this is like a monomial, right? x1, x2, x4, and this is like x1, x3, x4, let's say. So then the quadratic degree is actually saying what is the Hamming distance between these two. If you look at them as vectors, or you can look at them as some some vector form, then what is the Hamming distance between these two? So that is kind of alternatively, it's like the degree of the product of these two terms, or you could define it as the degree of the square of each line. They would all be the same measure. So, but ultimately, it's, I think, most interesting to look at it as Hamming distance. So, and the split is an operation which kind of helps to drop the quadratic degree of a proof. So where let's say you have a line like this, p1x plus p0, and suppose so like in the Boolean world we say set x to 0 or set x to 1, but here let's say we say split on x, then the proof we would replace each line, we would replace the line p of the proof with p1 p0. So we would break up the line into two parts. Okay. And we'll have to prove that this actually doesn't break the proof. It's a proper proof. It follows the rules and all that. But which he proved. And but ultimately, what you can notice is that this helps reduce the Hamming distance. Because if x is some variable which appears in a lot of pairs of terms, which is of large Hamming distance, then you're breaking it up so that the terms don't interact. So now all the p1 terms one side, p2, p0 terms are other side. So now the Hamming distance can potentially drop. Okay, so what Sokolov showed is again like a size quadratic degree trade-off. So that if there is small size, there is small quadratic degree, and it's very similar to size degree, and there's not much to talk about there. And but he also showed that actually low quadratic degree, with low quadratic degree proofs, you can apply a trick to get low degree proofs, which is a very simple trick. Like, which is what you do is, let's say you have this proof and you know it's low quadratic degree, right? Then you just take some term from this proof. Let's say you take t1, right? And you multiply this line with t1, let's say, and you make a new proof like that, right? And again, you have to show that the pieces come together. But if you do that, then you switch immediately from quadratic degree to degree, right? So okay. So yeah, so okay, so the last
Question of people who might leave, can we have a statement of the 9th theorem before they leave?
Actually, yeah, okay. Do I have this?
No, you have to do this before here.
Yeah. So
You can have an interview.
I didn't. Yeah, did I even? I don't know if I wrote this. I don't know. Okay. Which yeah, So okay, sorry. Maybe I can. No, so it's fine. So the thing is, I mean, I have a question here, which is also the answer. Like, so the thing is, there was so in Sokolov's paper, and then Razborov actually put it on his website of Open Problems, and where they asked this question that okay, we have PC plus minus one bounds now, right, due to Sokolov, right, and okay, but what can we say about these two systems now? Like we have PC01, PC plus minus one. So they asked, can you separate them? That is there a formula which is kind of, let's say, hard for plus minus one but easy for 0, 1, because the other way we know these parity equations and so on. Parity equations are hard for 0, 1, easy for plus minus 1. But can we do it the other way, or can we somehow simulate this 0, 1 with plus minus 1? So either way, and that's actually the lower bound, which the lower bound so my lower bound gives this tautology, which is easy for 0, 1. It has polynomial size in 0, 1, but it has exponential size in plus minus 1. So that would be the statement of my result. So okay. So
title itself is a statement.
yeah, I mean, yeah, pretty much. So, and in fact, reviewers pointed out to me that it's my result actually holds if you replace PC01 with resolution. So it's even slightly general that way, that it has small resolution size, which is a more like a stricter measure than PC01, but it has large PC plus minus 1 size. So I guess I'll just give you.
So in other words, PC plus minus 1 doesn't even polynomially simulate resolution.
Yeah. It doesn't even polynomially simulate. So I'll just talk about. I guess I could go into the technicalities.
Is the other direction known? Does resolution simulate PC plus minus 1?
No, it doesn't, because you have this let's say Gaussian elimination is hard for resolution, easy for PC plus. Sorry,
so it's incomparable.
Yeah, incomparable. Yeah. So that, which is the title of the paper. So I'll give you the basic intuition. So the basic intuition is very simple, that if you take the OR function over n bits, right, it's small size over 0, 1, right? It's one gate or one. But it's exponential over plus minus 1, in the sense that if you want to write a polynomial, plus minus 1 polynomial computing OR, you can easily show that.
I don't know. What are small size? What do you mean? You have exponential size. You mean under generalized monomials or what?
No, over 0, 1, I mean, or Boolean.
Yeah, but if I want to express the OR function as a
yeah.
basis.
No, with negations, negated literals, negated variables. Yeah, dual. Yeah. So you need to use, if you used variables for the negations as well, then it's a small size. But if you for plus minus 1, we can easily show it's large size. So you can think of this result as an extension of this, but for proofs, right? So we know this for functions or polynomials, but now this result is just saying if you even write proofs with these polynomials, it's still, this intuition holds, and you can prove it. And even the tautology which I use is basically some tautology which is easy over 0, 1, but it's lifted with an OR. It's lifted with a small log size OR. So in order to sort of accentuate this difference, in the sense that because the really core of the lower bound has to come from this basic intuition. So using an OR gadget highlights that. So, but maybe, okay, I'll just briefly say something that the main difficulty was that so initial idea would just be what I said, that take some tautology with small proofs over 0, 1, maybe lift it with an OR and expect lower bounds. But what if the 0, 1 proof itself has many negated variables, right? So then what happens is, even this OR will blow it up. So let's say you use a 2-bit OR, and your proof is somehow expressing the negation of these many variables. This is already exponential size, right?
For 0, 1 itself.
For 0, 1 itself, right? Because negation and the OR, they'll blow up over 0, 1 itself. So then the main trick was to look at these formulae, which already have been looked at, which they have a small positive resolution refutation, which is a notion which people have already looked at, which basically says that the proof has only every clause has only few negated literals, right? It has maybe 1 or 2 negated literals throughout the proof, but literals are positive. So, and there is this tautology. So maybe I can just mention this tautology that it's called linear ordering principle, which says that linear ordering principle essentially says that every linear order of elements has to have a minimum, right? So, and or we can take the negation and claim that there is an ordering where every element has a lesser element. And people showed that linear ordering principle. So once upon a time, it was a conjecture that linear ordering principle was hard for resolution. But Stalmark, he showed that not only is it easy for resolution, but it is also a positive proof. Like it has a positive resolution proof in the sense that most literals in the proof would be positive, right? And this was again used by Susanna, Jacob, and some their group interestingly to separate the PC size from PCR size. So PC is without what is like when you mentioned without dual variables, and PCR is with dual variables. So they sort of use this linear ordering principle, and maybe also they used an OR or something. I think they also used an OR gadget, something like that, to get this separation. So this was really kind of what was looking good for this lower bound, and following this sort of a path was what ultimately led to the lower bound. And yeah, I think I don't have much to say other than this. I mean, the rest is all technical details about what is the linear ordering principle and how. What is this notion of some special notion of degree I had to define to in order to capture this intuition, which kind of takes care of this OR. So it forces this. The fact that there is an OR and something like that. So, but yeah, other than that, so maybe I can just jump to open problems and conclude. So,
Sorry, so just one.
Yeah.
Did you say that roughly your proof basically is saying that if you had a small 1 minus 1 PC proof,
yeah,
then eventually you would be able to compute the OR function of a large arity with small
no, sorry, I didn't get. No, if you have a small plus minus one proof, no.
If you have is your proof sort of saying that if you have a small polynomial calculus proof over 1 minus 1 for the linear ordering principle lifted with your gadget,
yeah,
then it would mean that
somehow you're
you can represent the OR using small sparsity in the Fourier.
No, it's not that it's not that strong or that direct. But I think it's not that weak. Also, it's somewhere in between. Like you could somehow indirectly conclude that, but not this straight connection that clearly. Or sort of an interpolation theorem, or like how interpolation theorem you say if there is a short proof, then you can interpolate, you can get a like for cutting planes, you can say a short cutting planes proof implies a monotone, such small monotone circuit. So it's not that strong a connection, but intuitively, if you dig into the proof, that's what is going on. Kind of that's where the blow up is coming from. So intuitively, so I can just mention what exactly it is saying about the OR. So what it's saying is that any proof of this linear ordering principle lifted with OR has to have sort of, in addition to the usual degree notion, it has to have this other degree notion, which where say you take the OR gadget, then all variables of the OR gadget have to appear in your term. So either your term is clearly high degree, or if it is low degree, then the gadget has to appear in full, like for many variables. So I mean, that's in a sense, I don't know. I mean, it's not very direct, but in a sense, yeah. So in a sense, you're saying that because the gadget has to appear in full in many terms. That means you're saying, and the gadget is an OR, so that's where the sparsity connection is coming from, because you're forcing the gadget to appear in these terms. So okay, so maybe I can just conclude with some open problems. So yeah, so basically there are few open problems is can this result be extended to any tautology with a small positive resolution refutation? So there is one tautology or other tautology which is PHP with exponentially many pigeons. So Bus Pitasi, they used it to separate I think no, they used it to show. Sorry, I forget. I think they used it to show that basically PHP with exponentially many pigeons, you cannot prove PHP lower bounds. So resolution lower bounds for PHP say that PHP with n holes n plus 1 pigeons is hard for resolution. But if you take like n holes and let's say 2 to the n pigeons, then that PHP is it in fact has a polynomial size in resolution. So that, and there they used this somehow that PHP has these I think they called it monotone resolution proofs. So could it be that for any such thing with monotone proofs or positive proofs, this my result can be extended like for example this thing. And the other thing which we are actually currently working on is can we extend this to SOS? So again with SOS, so in Dimitri's original paper he defined SOS plus minus 1, and he actually also gave lower bounds for SOS plus minus 1. And now the question again is can you separate SOS plus minus 1 and 0 1, which it seems much tougher because the same formula linear ordering principle, there are degree lower bounds due to Aaron Potechin, but those degree lower bounds are much more involved than what we have for this LOP and PC lower bounds. So they are very much they use a little bit of representation theory apparently so they are not that simple that we can, yeah, at least we are trying, but yeah. So and lastly there has been so I talked about this system AC0 parity Frege. We are very far from getting lower bounds for that. But what currently people are looking at is the subsystem of this AC0 parity Frege, which is resolution over parities, which I think Arkadev and his student has been, they have been looking at, they have some lower bounds for like a subsystem of this thing. And even others have been working on this. But currently we are again stuck at subsystems of this resolution over parities, but not the general system. So general system again seems wide open, but can we prove lower bounds for this using OR lifted tautologies? Because what Arkadev's results and other results have proved lower bounds for these lifted tautologies, which are like majority gadgets or which are some gadgets like that, right? I think they call stifling gadgets, which so some gadgets with some particular like strong gadgets. But can you take a simple OR gadget and lift a tautology and can you get lower bounds for res parity? Maybe even a subsystem. Okay. So yeah, that's a right control.
Questions? So I was a little confused about the split process. So I mean your polynomial looks like, let's say, P1x plus P0.
Yeah.
And you replace this, I mean, or rather you from this you just derive P1 and P0.
I mean, you don't derive it, sort of you kind of shift to this proof. So let's say let's say okay. So let's say you have this is your whole proof, right? And let's say each Pi is let's say Pi1x plus Pi0. Then you just shift from this proof to this proof, which is Pi1 equal to 0, Pi0 equal to 0. Or, I mean, I can write it actually. So P1 equal to 0, P1 0 equal to 0, like P2 equal to 0, P2 0 equal to 0, and so on.
Oh, you just do the argument on this this other proof. Because it's not like you can derive those two lines from this somehow.
No, so that is the interesting thing about plus minus 1 is that if you these two lines have exactly the same information as this line. So
it may have the same information, but it's not the same solution set.
What
I mean, in the sense that it's not that whenever I have if I have a particular common solution
to
one set of polynomials,
Yeah.
It's not like that is a common solution for this new set of polynomials.
Oh, yeah, no, because obviously X is missing.
No,
but,
yeah, but even,
I see. Yeah, no, yeah, you're right, yeah.
okay,
Um,
okay,
yeah, but, yeah. So, no, it's kind of an abrupt switch, like it's not smooth in the sense that you can derive. So that is definitely the
Okay.
case, yeah. So, and you also have to go through some trouble to prove that you have your tautology, and that doesn't break when you make this switch. So because that also you have to sort of apply this split somehow to that and then make this whole thing consistent. So that's where most of the complexity is, that your tautology information. So any other more questions? Not that's fine. Prashant,